Hey everyone, welcome back to the channel. If you've watched any of my recent videos, you know AI is all about vectors these days. But here's the real challenge nobody talks about: scaling vector infrastructure at production scale. Whether you're building a semantic search engine processing 10,000 queries per second, a chatbot with long-term memory using retrieval augmented generation, or managing billions of embeddings for enterprise AI, scaling vector databases is not as straightforward as adding more servers. Today, we're diving deep into the real-world pain points engineers face when scaling to billions of vectors and, more importantly, the practical solutions being used by industry leaders like Pinecone, Weaviate, Milvus, and Qdrant. By the end of this video, you'll understand exactly where vector systems break down and how to fix them. Let's start with the big picture. When you're building your first vector system with thousands of embeddings, everything feels smooth. Queries return in milliseconds, memory usage is minimal. But then your startup scales. Suddenly, you're handling millions of embeddings, then hundreds of millions, then billions. And here's what happens. The performance curve looks deceptively smooth until it doesn't. It collapses. Let me give you concrete numbers. 1,000 embeddings, you're getting queries back in about 1 millisecond. Everything's great. Life is good. 1 million embeddings, now you're looking at 50 milliseconds per query. Still acceptable, but you're starting to see the stress. 1 billion embeddings without optimization, you're talking 10,000 milliseconds. That's 10 full seconds per query. That's unusable. Why does this happen? Because vector similarity search fundamentally requires high-dimensional mathematics. As your database grows, the computational cost grows exponentially. There are 3 critical areas where this breaks down. First, storage and retrieval speed. How do you store billions of vectors and still retrieve them quickly? Second, compute efficiency and latency. The math itself gets more expensive. How do you handle that? Third, consistency and index management. When you distribute billions of vectors across multiple servers, how do you keep everything in sync? Let's tackle each pain point one by one. All right, let's dig into the real problem: high latency with large-scale searching. Imagine you have 1 billion embeddings. Each one is a 1,536-dimensional vector. That's how many numbers OpenAI's text embedding model outputs. Now someone queries your system. Find documents similar to this. Here's what a naive engineer might do. Okay, I'll just calculate the distance from the query to every single embedding in the database. That's simple, right? No. That's 1 billion distance calculations across 1,536 dimensions each. That's 1.5 trillion mathematical operations per query. That's not seconds. That's over 25 minutes. This is the curse of dimensionality. As dimensions increase, distances become less meaningful. Every vector is equally far from every other vector in high-dimensional space. Your search space explodes exponentially. So what's actually happening in production systems that are failing? First, they're using brute force or exact nearest neighbor search. Calculate distance to everything, return the closest. Second, they're not using approximate indexing methods like HNSW, IVF, or product quantization. These are algorithms specifically designed to handle high-dimensional search efficiently. Third, they're misconfiguring query parameters, setting search radius too broad, wrong recall settings, no tuning for their actual workload. The results? Queries timing out, users getting frustrated, infrastructure costs skyrocketing. Okay, enough doom and gloom. Here's how you actually fix this. The solution is Approximate Nearest Neighbor Search, or ANN for short. The key insight: you don't need the exact nearest neighbors, you need the approximate nearest neighbors really fast. HNSW, Hierarchical Navigable Small World, is the gold standard here. Instead of checking a billion vectors, HNSW creates a hierarchical graph structure. When you query, you navigate this graph intelligently. The time complexity drops from O of n, linear with the number of vectors, to O of log n, logarithmic. Let me make this concrete. With a billion embeddings, brute force, 1 billion calculations. HNSW, about 30 calculations. You just went from 10,000 plus milliseconds to under 50 milliseconds while maintaining 98 to 99% accuracy. Now let me show you how this actually looks in code. I'm using Milvus here, but Qdrant and Weaviate work similarly. The beauty of HNSW is that it's probabilistically guaranteed to find a very good approximate nearest neighbor while doing a tiny fraction of the work. But HNSW isn't the only option. You've also got IVF, inverted file indexes, combined with product quantization. IVF first partitions vectors into clusters, then only searches within the closest clusters. Product quantization compresses vectors without losing much information. The trade-off table on your screen shows the comparison. HNSW gives you near-perfect accuracy with speed. IVF plus PQ sacrifices a tiny bit of accuracy but uses even less memory. Beyond the algorithm, here are practical tweaks that work. Cache common query embeddings. Your users probably ask similar questions. Use Redis or an in-memory cache to skip the index lookup entirely for repeated queries. Tune HNSW parameters. M controls connections per node. EF construction controls how hard you work when building the index. EF controls search effort. These matter hugely for your specific hardware. You're going from unusable to production ready with these changes. Great, so you've optimized queries. Your latency is down, but now you're hitting a new wall. You've got too much data for a single server. Time to scale horizontally. You split your billion vectors across, say, 100 servers. Each server handles 10 million vectors. Now you've got sharding and replication bottlenecks. This is where distributed systems get messy. Here's what typically goes wrong. Problem number 1, unbalanced shards. You randomly distribute vectors to servers, but vectors aren't uniformly distributed. Maybe all your vectors are about a specific topic that clusters together. Server number 42 gets way more queries than server number 23. Suddenly, server number 42 is at 90% CPU utilization, while server number 23 is sitting idle at 15%. Your bottleneck is that one hot server, and you can't scale horizontally anymore. Problem number 2, replication lag. For fault tolerance, you replicate each shard to multiple servers, but replication takes time. Write vector v to server A, it propagates to server B, but there's a 500 millisecond lag. A query hits server B before the replication completes. You get inconsistent results. The same query returns different results on different replicas. Your system is correct, but users see bugs. Problem number 3, data locality. Your query servers are in region A. Your vector storage is in region B. Every query traverses the network. Network round-trip time adds 50 to 100 milliseconds per query. This compounds. And here's the cascade effect. Poor locality leads to more network hops. More hops means higher latency. Higher latency means timeout. Timeout means retry. Retry means even more load on the network. It's a death spiral. The fix is actually elegant, smart sharding strategy. Instead of randomly distributing vectors, use semantic sharding. The idea, vectors that are similar should live on the same shard. How? When building your index, cluster similar vectors together, then assign each cluster to a shard. Now when you query, similar vectors are co-located on the same servers. Fewer network hops, fewer hotspots. This is a game changer. It's not just about even distribution, it's about query-aware distribution. Second strategy, co-location. Keep compute, storage, and index together. Use Kubernetes pods with local NVMe storage. The index is loaded in memory on the same machine as the query processor. Zero network latency. Compare this to the old way. Query hits server A, which has to fetch index from server B over the network, then compute locally, then return. That's network latency baked in. With colocation, it's all on one machine. Local memory access is nanoseconds. Network access is milliseconds. That's a million times difference. Third strategy, load-aware auto-scaling. Monitor CPU, latency, and throughput per shard. When a shard gets hot, automatically rebalance by moving some vectors to a new server, or clone the shard and route some queries to the replica. This is what Pinecone does automatically. This is what Qdrint's clustering mode does. Together, these three strategies solve the sharding problem. You go from one hot server tanking everything to balanced load across all servers with minimal network traffic. In practice, companies like Lyft, Square, and others using vector databases at scale have reported 3 to 5x improvements in query latency just by optimizing sharding strategy. Here's a frustrating one that engineers encounter constantly. Your vector database is using 90% CPU, but only achieving 500 queries per second. Something's deeply wrong. At 90% CPU, you should be handling thousands of queries per second. This screams suboptimal indexing or threading. Let me break down what's usually happening. Root cause number 1, exact distance computation. Even though you deployed HNSW, you're computing exact distances during the graph traversal. You should be using approximate distance calculations or pre-computed lookup tables. Computing Euclidean distance in 1536 dimensions. That's 1536 multiplications, 1535 additions, 1 square root, per vector, per query, thousands of times per second. That adds up fast. Root cause number 2, thread pool wastage. Your server has 32 CPU cores, but your thread pool is configured for 4 threads. 9/10 of your CPU sits idle. Meanwhile, your 4 threads are maxed out. This is shockingly common. Default thread pool sizes are often 2 or 4, not based on actual core count. Root cause number 3, dimension mismatch. Your embedding model outputs 1536 dimensions, but your index was built with a different model that outputs 384 dimensions. The system is padded vectors to match, wasting CPU on meaningless calculations, or it's recalculating dimensions on the fly. The fix is surprisingly straightforward. Tune HNSW parameters. M controls how many connections each node has in the graph. Higher M equals better search quality, but higher CPU per query. EF construction controls how hard you work when building the index. Lower values build faster, but create lower quality graphs. EF controls search effort at query time. This is your main lever for throughput versus accuracy trade-off. If you're at 90% CPU with low throughput, try lowering M from 30 to 16, lowering EF construction from 500 to 200, lowering EF from 200 to 100. You might drop from 99.5% accuracy to 98% accuracy, but 98% accuracy is still great for most applications. Parallel query execution. Ensure your query processor actually uses all available CPU cores. This single change can give you 8 to 32x improvement on multi-core systems. Result, you go from 90% CPU/500 QPS to 70% CPU/5000 QPS. That's a 10x improvement in efficiency. This is not theoretical. This is what companies are doing right now to handle production workloads.
Here's one that catches people off guard. You've got 16 gigabytes of RAM available, but only 2 gigabytes is used. Yet your system is constantly hitting disk. Disk IOPS are through the roof, queries are slow, CPU usage is high waiting for disk. What's happening? Your indexes aren't preloaded into memory. Vector databases store data in 2 places. 1, hot storage, the index structure kept in RAM for fast access. 2, cold storage, the full vectors kept on disk. If your indexes are constantly paged out to disk or only partially cached, every query becomes a disk operation. And disk is 10,000 to 100,000x slower than RAM. This problem manifests as high latency, P99 queries taking seconds instead of milliseconds, high disk I/O, SSDs degrading, costs spiking, unused RAM. It's sitting there but not helping. Why does this happen? Over-partitioning. You split data into 1,000 shards to distribute load. But now the index is so fragmented that most of it doesn't fit in RAM. Misconfiguration. The system defaults to lazy loading indexes, only load from disk when needed. No hot data strategy. You treat all vectors equally, but 80% of your queries are for 20% of your vectors. That 20% should stay in RAM permanently. Here's the fix. Preload indexes at startup. Tell the vector database, on startup, load the complete indexes into memory. Don't lazy load. This adds 30 to 60 seconds to startup time, but pays dividends forever. Selective caching. Identify which vectors are queried most often. Keep those in RAM, let others stay on disk for cold access. Monitor cache hit ratio. You want cache hit ratio above 90%. If it's below 50%, something's broken. Result? You go from 2 GB used, 10,000 disk IOPS, slow queries, to 14 GB used, 1,000 disk IOPS, fast queries. More RAM utilization, better performance, same hardware. This pain point is subtle but devastating. Index synchronization and reindexing. Here's the scenario. Your embedding model gets updated. You trained a new version that's better at capturing semantic meaning. It outputs slightly different vectors. You release the new model to production. New documents are indexed with the new model. But your old index, it still has vectors from the old model. Now when a user searches with a query embedding from the new model, it gets compared against index vectors from the old model. You're comparing apples to oranges. Results are garbage. Or worse, you realize your index is corrupted. It has vectors from both the old and the new model mixed together. Full reindex needed. But a full reindex takes 4 hours on your hardware. You can't go offline for 4 hours, so you try to patch it incrementally. But now you've got consistency problems. This is the index synchronization problem. The challenge, you need fresh indexes, but full reindexing is expensive and causes downtime. Here's how companies actually solve this. Incremental delta indexing. Instead of rebuilding the entire index, just update the changed vectors. Every day, you only index the new vectors added that day. Takes minutes. Every month, you do a full rebuild during a scheduled maintenance window. Takes hours, but only happens monthly. You get fresh indexes without constant pain. Versioning and rollback. Tag each index version. If you deploy a new index and it's broken, roll back instantly to the previous version. Takes seconds. This is critical for production systems. Data lineage tracking. Know which model version created which vectors, so you can trace bugs. Did a query return wrong results? Check which embedding model was used. Was it the old model or new model? That tells you immediately if you've got a version mismatch. With these strategies, index updates become safe and fast. No 4-hour windows, no inconsistency, no panicked rollbacks at 3 a.m. All right, let's talk about the money part, because for many teams, this is the biggest pain point. Vector workloads burn 3 things: memory for indexes, CPU for queries, and storage for vectors. Unoptimized systems often cost 3x more for the same throughput compared to well-tuned systems. Let me give you realistic numbers. Let's say you're running a system with 1 million embeddings at 1,536 dimensions. Raw storage. 1 M vectors times 1,536 dimensions times 4 bytes per float equals 6 gigabytes. Index overhead. HNSW indexes need extra structure. Call it 3 gigabytes.
Total storage, 9 gigabytes on disk. That's maybe $30 per month on cloud storage. Compute, handling 1,000 queries per second, assuming $50 per 1 million queries. That's $50 per month. Network, inter-region data transfer, caching infrastructure, etc. About $20. Total, $100 per month for a well-optimized system. But if you do it wrong? Bad storage, no compression, redundant copies, inefficient sharding. Now it's 30 gigabytes, $90 per month. Bad compute, inefficient indexing, no parallelization. You need 5x more servers to handle 1K QPS. Now it's $250 per month. Bad network, no data locality, constant cross-region transfers, $50 per month. Total, $390 per month for an unoptimized system. Same throughput, 4x the cost. Scale this to companies handling billions of vectors, and we're talking millions of dollars in difference. How do you optimize for cost? Strategy 1. Auto-scaling. Scale compute up when you need it. Scale down when idle. You only pay for what you use. Strategy 2. Vector compression. 32-bit float per vector is massive. Quantized to 8-bit, 75% savings. Quantized to 4-bit, 87.5% savings. Modern quantization techniques maintain 95% accuracy while using 1/8 the storage. Strategy 3. Managed services. Run on Pinecone, Qdrint Cloud, or Weaviate Cloud instead of self-hosting. They handle infrastructure optimization. You pay per query or per gigabyte stored. Often cheaper than managing your own cluster. Result? Cut infrastructure costs in half or more. Keep the same performance. Okay, we've covered 7 pain points. That's a lot. But there's actually a simple playbook you can follow to prevent or fix all of them. I call it the Optimization Playbook. Step 1, profile first. Before you optimize anything, measure where the problem actually is. Use APM tools, log query latencies, monitor CPU, memory, disk I/O. Identify the bottleneck. Don't guess, measure. I've seen teams optimize query algorithms when the real problem was memory allocation. They wasted weeks. Step 2, algorithmic changes. Once you've identified the bottleneck, switch to the right algorithm. If latency is high, use ANN, HNSW. If storage is high, use quantization. If throughput is low, optimize index parameters. This is where most of the gains come from. Step 3, hardware optimization. Co-locate compute and storage. Use local NVMe for hot indexes. Consider GPUs for distance calculations. Sometimes you need better hardware, not better code. Step 4, system-level tweaks. Adjust thread pools, balance shard loads, implement caching, tune batch sizes. These are the detailed optimizations that take 90% systems to 99% systems. Step 5, monitoring and observability. Track metrics continuously. Query latency, P50, P95, P99. Throughput, QPS. CPU and memory per node. Cache hit ratio, disk I/O, index size. If you're not measuring it, you can't improve it. Step 6, iterate. Optimization is never done. Make a change, measure the impact, iterate. Some teams do this monthly. Good companies do it weekly. Excellent companies do it daily. Vector databases are now the backbone of modern AI. From LLM applications to recommendation systems to semantic search, vectors are everywhere. But scaling them requires strategy across every layer: algorithm, index, hardware, system, operations. There's no silver bullet. It's about designing a balanced system where each layer works well together. Here's what I want you to remember. First, measure first. Don't optimize what you haven't profiled. Guessing wastes time. Second, Think holistically. A fast algorithm means nothing if your hardware setup is bad. Every layer matters. Third, iterate continuously. Scaling is never done. It's ongoing optimization. What works today might break tomorrow when you scale 10x. Thanks for watching. If this deep dive was helpful, smash that like button and subscribe for more AI infrastructure content. All right, I'll catch you in the next one. Keep scaling. Cheers.